Let's continue on and move on to a different item here. We've talked about structural hazards, and now we're going to move on and talk about data hazards. OK, so what is a data hazard? So a data hazard occurs when you have one instruction that depends on the data of a previous instruction, or a previous data value. Sorry, a previous data value. Depending on a previous instruction is not precise enough. We want to depend on a previous data value, or a data value that's generated by a previous instruction, which is still in the pipeline. And like structural hazards, data hazards also have a couple different approaches, which we will not talk about all of them today, but let's start talking, let's introduce them at least. First thing is you can schedule around it. OK, so what does this mean? Well, let's say we have a processor pipeline, and the processor pipeline is generating values. And we have one instruction which is dependent on another instruction, but the first instruction, let's say, takes a couple cycles to generate that value. The value won't be ready, so you can't go and issue a subsequent instruction. So we have a data hazard here. We have a data dependency hazard. So you could schedule around it. So you could, for instance, introduce no operation instructions into your instruction sequence and have the programmer avoid the hazard if the programmer knows the microarchitecture of the machine. And this is actually showed up in some early processors. A famous example of this is at the floating point unit for the Intel i860, which is an old sort of early RISC architecture made by Intel. And in the i860, the floating point unit was not interlocked. So if you execute a floating point instruction, and then you have another instruction which is coming down the pipe which uses the result of that, you might get the wrong value. So it was the programmer's responsibility to make sure that didn't occur, and you actually put in no ops there. The next approach, which we'll be talking more about in today's lecture, is to stall. So if you have a data dependence, you can actually stall stall later instructions dependent on earlier instructions. And some of the important thing here to note is you're going to freeze the pipeline until the preceding instruction has generated the value, but hardware does this freezing. So the hardware does the freezing, and we're going to develop this more today, but you actually have to freeze everything before that instruction. You just can't freeze the dependent instruction. And that's because the sort of traffic behind it will catch up on the earlier traffic and sort of pile up into it. So if you want to make a pipeline which works out like this, you're going to actually want to stall everything earlier. And we'll look at the wiring that you need to do that. Another solution is you can bypass. So what this is, an example of this is you can add extra hardware to your data path. And the extra hardware is going to send the value as soon as it gets created. So you may not have to wait for it to get to the end of the pipeline. So if the data value gets made early, you can just forward that to an instruction which needs it, but that adds extra hardware and complexity to your design. And finally, we're going to talk about, not in this lecture, this is the one thing, the solution we'll talk about later is you can speculate. So if you have a data hazard, you can assume it's not a problem. Or you can assume that, everything's going to be OK. I'll just use the incorrect value for a little bit of time, and we'll assume that the old value is equal to the new value, or you can do data speculation. There's other ways to do this. And if you make a mistake, you catch it by the time you get to the end, and you basically have to re-execute the instruction with the correct value then. So you can do speculation. And this is kind of like a big guessing game here. But this is used in out-of-order processors in multiple different ways. And we'll be talking about that in a couple lectures from now. OK, so let's look at an example data hazard executing on our processor pipeline. So we have two instructions here. We have an add with an immediate of register 0 plus 10 into register 1. So we're going to be using in this class the notation where the leftmost operand, or the leftmost register, is the destination, and the right operands are the input or the source operands. So we're going to add 10 plus 0, R0 and MIPS R0 is hardwired to 0. And we're going to add that into R1. And then this next instruction here is going to exhibit a read after write data dependence. And this read after write data dependence, we have an add I, and it's going to just use exactly this value, which gets created the instruction right before. So this is going to take R1, add 17 to it, and deposit it into R4, or register 4. But we have a little bit of a challenge here because it uses the result of the instruction right before it. OK, so what happens in this design? Let's say our instructions are marching down, and we have the first add here, and the second add's back here. OK, nothing bad's happened so far. Now the first add goes here, and the second add is here. OK, nothing bad has happened so far. But the question is, what do we fetch out of the register file for the second add? Because the result of running R1 is available here, but it hasn't made it back into the register file yet. So it's actually going to fetch the old value. That's not good. So if you were just to play this without any stalling or interlocking, you'll actually have this instruction read the old value of this instruction, the second instruction, read the old value of R1 and not the new value that we want it to read. So we need to think about this a lot harder. Yeah, R1 is stale. Oops, we made a mistake. So how do we go about resolving these hazards? Well, we want to somehow detect them, these data hazards, and then we want to feed this information back. And later stages provide dependence information to earlier stages. So this is a later stage, this is an earlier stage, and we're going to feed information back here. And depending on that information that is fed back, we're either going to stall or kill instructions. So the most basic example here is we're going to have stage 4 influence stage 3, and it could say stage 3 can make some decision based on that and maybe stall or kill instructions. And likewise, stage 3 will influence stage 2, and stage 2 will influence stage 1. But this is not really good enough, because let's say stage 4 tells stage 3 to do something. If stage 3 doesn't tell the earlier stages, we're going to get a pile up. Like cars are going to pile up here all into stage 3. So this typically means that you need some higher level sort of feedback here where you have stage 4 giving information to all the previous stages, stage 3 giving information to all the previous stages, and vice versa. So you'll actually be able to provide information to all the previous stages, and then everyone can make a decision based on this. And what's really important here is controlling a pipeline like this basically requires that controlling a pipeline like this is really important, because if you don't, and if you have sort of feedback going the other direction, you might end up with some form of deadlock in your processor. Because if you have a early instruction which is dependent on a later instruction, then you might have that resource may never get free because the later instruction might be dependent on the earlier instruction and vice versa, and all of a sudden you have a sort of a big cycle and everyone's dependent on everyone and the machine just stops. So it's really important that when you're doing this that stage I+1 only feeds strictly information back to stages 1 to I. OK, so let's resolve some data hazards and look at how we would actually do this on our simplified pipeline here. We're going to use the same example case here. We have 2 adds, and we have a dependence between R through register 1. So the first thing to realize that we're going to have to do is we're going to have where do we need to stall the pipeline? Or where do we need to stop the pipeline or interlock the pipeline? And when we were looking at these 2 adds, it wasn't a problem until the second add went to go and read the register file here. If the first, if we didn't read the register file until later, this would not have been a problem because the value might have been up to date. But because we read it so early here, we've pipelined sort of when data gets computed and when it gets written back and read into different stages, we have this challenge. So what we're going to do is we're going to stall here and reread the register file over and over again until the first value of R1 gets written into the register file. Unfortunately, we're going to be waiting a while here because we don't write the register file here. We don't write the register file here. We write the register file here through that wire. So we might we're going to stall multiple cycles here. So when we're doing the stalling in this stage, we're going to want to think really hard about what should be going down the pipe during that time. Well, we've stalled instruction, the second add here, this is, instruction 2 here, and instruction 1 just keeps flowing down the pipe. So we don't want to stall these later stages. We only want to stall this stage, and we need to stall the previous stages so instructions don't pile up into us. Now, how do we go about, from a wiring perspective, executing instructions and sort of having the first set of instructions clear out of the pipeline? Well, we're actually going to insert a multiplexer here on the instruction register side of things. And this multiplexer is going to insert no-op instructions or no-operation instructions. We're actually going to be inserting bubbles into the pipe right here so that the first instruction, the first add, can clear out of the pipe. And we know what's executing here. Because we don't want to accidentally have the second instruction start executing even though it's stalled here, because then it's going to possibly change state as it goes down the pipeline. And it'll also affect sort of dependency calculations here. So we want to insert no-ops. And the stall condition, as I said, goes to the program counter, the instruction register, so these flip-flops before the stall point. And it's also going to go into the select line on this multiplexer to choose to insert no-ops. OK, so that's the beginning of this. And I wanted to just say this is sometimes called interlocking or interlocks. Is an important nomenclature here that you're interlocking the execution of the instruction here, and depending on the other ones, and you're actually checking that. So sometimes people call stalling interlocking. OK, so let's draw a pipeline diagram of what's going on here. So we're going to plot time on the x-axis and instructions on the vertical axis. And we'll look at the resource graph also. OK, so we have our first instruction going on the pipe here. It takes register 0, adds 10 to it, and it's going to go fetch, decode, execute, memory, write back. Second instruction starts going down the pipe here. Third, fourth, fifth. Well, you're going to note something here is we've stalled and the pipeline because we need to wait for the first instruction to write back to the register file before we can go read the result or read that value from the register file. So we strictly have to have this instruction here, the second instruction, the dependent instruction, in the decode stage and read the register file here on the cycle after the write back occurs. And we detect this stall condition this whole time, as denoted here with the nice purple box. And as I said, we need to stall earlier instructions. So this does install not only instruction I2, but installs instruction I3, because it's in an earlier stage in the pipe and it needs to be stalled. OK, so we could also graph this the other direction. And the reason it's useful to graph the other direction is you can see where no operations get inserted or no ops get inserted. So here we plotted the other direction with time versus stage of the pipeline or resource. And you can see we can see what's in the different stages and at some point here, there's nothing in these stages. Instead, we've actually inserted no ops. And it comes from the fact that we basically have I3 sitting in the instruction fetch for 3 cycles and I2 sitting in the decode for 3 cycles. And the later stages of the pipe get no ops inserted, and that's what that multiplexer is doing. So now that we've talked about how stalling happens in a pipeline diagram, let's move on and look at what the logic looks like inside of this. So here we have our data path for our stall, our data path for our 5-stage pipe. And in stalling, what we're really trying to do here is detect the case when a earlier instruction writes a register which a later instruction is going to use. So in this case, we are going to detect if a instruction in the decode stage is reading a value which an instruction in the execute, memory stage, or write back stage writes. So an uncommitted instruction writes to a register, and a previous instruction here, or excuse me, a later instruction goes and reads that, and we stall at the decode stage. And when we stall, we're going to actually want to stall everything behind it, as we had sort of already talked about here. OK, so let's start calculating this signal here. We'll call it, it's a control signal, so we'll call it C. We'll call it C stall. So we'll draw a little blob up here. We'll call this the stall calculation. And what goes into this calculation? Well, it's sort of a complex calculation. But the first thing we're going to want to check is we're going to want to check the destination for the operand. So we're going to check the destination for in some instruction that was an earlier instruction. And this is the register identifier, not the data value, but instead the register identifier. So this would be RD in a typical MIPS instruction. And we're going to compare that, and we're going to call that WS in this calculation. And we're going to compare it to the two source inputs here, or the source operand register identifiers. And these are both, because there's 32 registers in MIPS, these are all 5-bit values, all 3 of these values. And we're going to wire that all into our stall control unit here. OK, and if we get a match, the most basic thing we're going to want to do is we're going to say stall everything earlier and insert no-op instructions later down the pipe. So the stall is going to control a lot of things. It's basically control the front end of the pipe. And it's going to disallow an instruction here from moving forward in the pipe if anything in these later stages has a same destination operand. Or in this case, so far, we're comparing against just this location. So we're comparing against if the write back stage has the same register identifier destination as either of the two source operands for the instruction at the decode stage. OK, so what should we do should we just stall always if the RS fields, one of these source fields here or here, matches RD here, some RD? Should we just always stall in that case? Well, not every instruction is going to write a register. So what if we have an instruction, for instance, something like a store instruction, which does not write a register? So if we have a store instruction which does not write a register, we probably shouldn't be doing this compare operation, because we can have better performance if we don't stall under those conditions. And we're going to introduce a signal here called write enable, or WE. And WE is going to get wired into our stall calculation. Likewise, not every instruction reads both input operands. And a good example of this is an immediate instruction. An immediate instruction only reads one of the source operands, or source register identifier operands, and the other value comes from the immediate bits, which are in the instruction encoding. So this is going to introduce a read enable calculation here, because not every instruction reads a register. OK, so let's calculate this a little bit more here. So we're going to have something which calculates the destination, and I'll talk about what this blob is here in a second. But then we need to add, effectively, the write enable bits, or the write enable for this location in the pipe. And we need to add these read enable signals here. And these get calculated from the instruction registers in the respective locations of the pipe. So some decode bits there happening. Or maybe it all gets decoded here in the decode stage, and then we just pipeline those bits forward. And we do this calculation here. And now we can say, well, if the instruction in the decode stage matches what is being written back, the write back value, then we stall. OK, that's close to our full solution. Let's talk about this circle here. What's going on in this circle? Well, what you might notice is something like a jump and link or a jump and link register have an implicit destination target. The destination is not actually encoded in the RD field of the instruction. So instead, we need to add a multiplexer here, which multiplexes from the bits out of the instruction register and just a hard-coded value of 31, which is going to denote register 31. And by doing that, we can handle jump and links and jump and link registers. OK, so to finish this out, we want to compare not against just in the write back stage of the pipe, but we want to compare in all three of these subsequent stages here, here, and here. So we add extra calculation logic here, which computes the write enable and the register identifier based on the instruction register. And this might just be generated early and then piped forward depending on your pipeline design. That's sort of more traditional pipeline control. And all of this right now is ignoring jumps and branches. If you introduce jumps and branches, things get a little more complicated, and we'll talk about that in the control section, or the control hazard section of today's lecture. So now let's go on and talk about different instructions and where they get their source operands and what is their destination operands. And if every instruction in something like MIPS has all sources and all dest's. So this is just summarizing up what I said before, is that not every instruction reads and not every instruction writes. So as we can see here, ALU instructions read 2 operands and write an operand, but something like a store reads 2 operands, writes no operand. Jumps, jump and links only write and don't read. So it's a mix and match even in something like MIPS. And one other thing I wanted to point out is where this is actually encoded in the instruction moves around a little bit. MIPS tried to make this relatively uniform, but there's some examples here where you see that the destination changes a little bit between immediates versus non-immediates. And this is just because they didn't have the encoding space there to leave everything in a fixed location. Something writes a destination or not. And we have 2 things. We have the source, or the source operand identifier. And then we have the write enable, whether it is being written or not. And as you can see, there's a little case statement here dependent on the instruction type. And this is the instruction which is in the later stages of the pipeline that is executing. So we have, if it's an ALU instruction, it comes out of RD. If it's an ALU immediate instruction or load, it comes out of RT. If it's a jump and link, it's R31. And this says what you need to compare against. And then whether you need to write or not is a little bit complex here. If you have a ALU, an ALUI, or write, it writes it, except the case if the write source or the right number here, the right register identifier is 0. Because in MIPS, the 0 register is a throwaway register. You don't need to interlock against it. You wouldn't be incorrect if you did interlock against it. You just have slower performance. And then jump and link register always write, and then everything else doesn't write the register file. So this is sort of the first part of our calculation. And now we need to do the calculation of whether we actually read the value. And there's going to be 2 of these, one for the first operand, one for the second operand. OK, let's build up for the different instructions here. So we're just basically transforming this table into some logic equations that we're going to use. So ALU, ALUI, loads, stores, branches, they all read. Jump register, jump, and link register all read at least their first source operand. So RE1 gets set to true or 1 or on if it's any of these opcodes. But for jump and link, which don't read a first operand, that comparison has to not compare against this value. Otherwise, you'd be stalling too often. For the second operand, only true ALU instructions, so not immediate instructions, and stores read that second operand, and everything else doesn't. OK, so now let's put together the actual stall signal. And this is the stall signal for sort of the decode stage and the fetch stage of the pipe. And we're going to end up with the stall equaling a comparison between the source register identifier in the decode stage compared with the write register identifier in the execute stage, and that it's actually writing. Or we need to check with the memory stage. So it's the same calculation here with the memory stage. Same calculation here for the write back stage. And then we also want to make sure, so we take this whole expression and we AND it with whether we actually have a read enable for the first source operand. Because if we don't read the first source operand, there's no reason to stall for it. And we do a similar sort of thing here for the second source operand. We use RE2 that we derived here, and we AND it together with an expression which says, does the RT, the register identifier RT in the instruction, is it the same thing as the different destination register identifiers in the subsequent instructions in the different stages of the pipe, the later stages of the pipe? OK, so is this everything? This looks pretty complicated. And this is, well, this isn't so bad so far. If we make the pipe longer, we're going to end up with more terms inside of these two equations. Well, no, that's not quite the full story. So what are we missing here? Why else would we have to stall a pipeline? Well, unfortunately, this only takes into account instructions where the destination is available right at the end of the execute stage. Here and here, this encapsulates this. These two comparisons encapsulate that. Well, something like a load doesn't necessarily encapsulate that because the load value is not ready until all the way down here. So we might need to insert some extra stalls for that. Also, loads and stores are more complicated because you might have a data dependence through the data memory itself. So let's look at this example here. We have a little snippet of code here. We have a load, which is going to take, or excuse me, a store here, which is going to take register 2 and write it to some place in memory. And then we have a load here, which is going to read out of some place in memory and put it into register 4. OK. So the question comes up, is there any possible data hazard here? Yes, because what if R1 plus 7 is equal to R3 plus 5? So we're going to be having a case where you actually have two different values here, where one needs to pick up the data value of the previous store. So the load needs to pick up the data value of the previous store if and only if this is equal to this. OK, so that's not so bad. So let's look at these data hazards a little bit more and figure out how we can derive the equation to check for them. So just to recap here, our example is we have registers R2, we're storing it into a location here. and we're reading from possibly the same location. We don't know. So what if our 1 plus 7 is equal to our 3 plus 5? Well, first of all, we're writing and reading to the same address in time, right next to each other. Well, our hazard is actually avoided because our memory system is so fast. Because everything goes down the pipeline in order, we'll actually be able to write into the memory, and the next cycle we'll be able to read out of that memory, and we'll pick up the new value, pick up the changed value. But I wanted to introduce this because in more realistic memory systems, this requires much more careful handling. Because if you have a memory system which takes multiple cycles for the store to happen, or the store happens, let's say, at the end of the pipe into the memory, then you're not going to necessarily get that value. And you might need to bypass that, or you might need to do something more intelligent. OK, so we talked about stalling the pipeline. Now let's look at if we want to improve the performance some more. So one of the things that you may not have noticed in that stall, but did happen, is that if there were any instructions in the later portion of the pipeline, which an instruction at the decode stage was dependent on, it stalls. So no place do we actually forward the data values early. And now we're going to talk about forwarding or bypassing, of how to add extra data paths to allow a value to be sent from a later stage to an earlier stage faster than having to wait for the write back of the pipeline to occur. So here we have the bypassing, or here we have our data path that we had from before. And what I'm trying to get at is you have the problem that you have a value here, or you have an instruction here. And if there was any instruction which writes the writes to a operand register identifier that this instruction is going to want to read, it's going to stall. But as you might notice, a little bit of insight here is if you have an add, you can actually try to read this value early. But our data path is not good enough to do that right now. OK, so let's add in a bypass here. So we're going to add in this bypass, which takes the result of the ALU, turns it around, and puts a multiplexer here. And we can now detect whether, using sort of a similar sort of signal as our stall signal, we can detect whether two operands match. And if they do, we get the result value out of the ALU early and run it through this multiplexer. OK, so an important question is, does this help our example we had before from a performance perspective? So our stalling logic that we put in was good enough to make sure there wasn't an error. But it's not good enough to actually have good performance, because you have to wait for the value to get to the register file before you go ahead. So here we have the same example that we had earlier in class, where you have something which writes register 1 and something that reads register 1, and it's ALU add instruction sort of back to back. So does this get help? Well, yes. So this one, you can clearly see that this instruction is good. The result here is going to come back around, and we effectively don't have to stall the second instruction, because it can pick up the data value right then and there. The data value gets calculated in this stage. It can sort of loop around real fast here, and we don't have to stall at all in this case. OK, so quick quiz question here. Two other cases. We have a memory operation which writes register 1, and we have a jump and link, and then an add. Does this bypass right here help with these two cases? Well, we said it helped here. This case here. Well, when is the memory load, this is a load, when does the load result get calculated? Well, the load result doesn't get calculated until the output here of the data memory, or right here. So all of a sudden, that's after this bypass. So it's too late. So we still need to stall the pipeline here for load with a dependent instruction dependent on the load. So we're going to stall there. OK, now a trickier one. Jump and link 500. And then something which reads R31. So a little bit of background here on the MIPS instruction set. Jump and link implicitly writes to register 31. It's the link register. OK, so that means we have a data dependence. Where does the jump and link, what gets put into R31? So it's the program counter, or the program counter plus 4 is what it's architected as in MIPS. You could probably build it either way, depending on how you do jump register. So on first look, this looks like this should actually solve a lot of problems. We should be able to just bypass our result of our jump and link right to where it needs to go. It's a little unsatisfying, though, because if you look at the rest of the pipe here, if you have a jump, let's say in the execute stage, is the consumer of that instruction going to be here or not? So this one's kind of a trick question. So does it help? Well, you could bypass out and around, but the thing after it in the pipe is probably not going to be the appropriate instruction. So if I were to answer this question, does it help? I'd probably say no, because at least in the pipe drawn here, you're not going to be executing the subsequent instruction or executing the, even if this is the instruction at 500, you're not going to be actually executing that. You'll probably have to sort of wait for that jump to resolve somewhere farther down the pipe and then go pick it up. So the bypasses don't always help, and especially in something where it's not a fully bypassed pipeline. OK. Before I move off this slide, I wanted to say that this is called bypassing. Sometimes this is also called forwarding values, and we're going to be using those terms interchangeably in this class. OK, so now we get more details here. We start to look at how to derive the bypass signal. And we're going to build this the same way we derive the stall signal, and we're going to take terms out of the stall calculation we had before. So if you will recall, we have the pipeline diagram here with the stall signal. We have stalled stages, and we end up having to stall in this case where we have a ALU op followed by an ALU op that's dependent. So each stall or kill introduces a bubble into the pipeline, and this is going to give us a clocks per instruction over 1. With that new data path, which bypasses out of the ALU into input operand A, we can see that we actually can remove all of these stalls and just do the bypassing. So it actually shrinks the time taken to execute this code. And this new data path is really a great thing here. This bypass has taken us from greater than 1 clocks per instruction to 1 clock per instruction. And we're actually forwarding out of the execution unit for 1 into the decode unit here, and it gets consumed here in the execution unit in time 3 for the instruction 2. OK, so let's derive the bypass signal. And we'll start off by looking at our original stall signal. So this is just the stall signal we had before. And first thing we're going to do is, if you look at this case right here where we compared the execute write destination to the decode first source operand, we don't need that anymore. We added a bypass, and we added a forwarding signal to handle that case. So we can just sort of put a line through that. OK, so the next question that comes up is, we had, in this diagram here, we added this multiplexer here. to choose between reading from the register file and reading the data which came out of the arithmetic logic unit. And we need to ask, what is the control on that multiplexer? Well, it's the exact same case that we just crossed out. When that case is true, we want to do the bypass. So we can just take those terms and put it here, and that's actually the control in the multiplexer, or a source here. Is this correct? Is this the full story? Well, unfortunately, no. It's close. It's really close. It looks like it should work. But unfortunately, only ALU and arithmetic logic unit immediate instructions can benefit from this. If you have something like a load, you need to wait for the data value to show up. So this a source here needs to have some component saying, make sure it's a load, or make sure it's not a load, if you will. And up here, we actually have to reintroduce that term, checking to see whether it's something like a load. So what we're going to do is we're going to split the write enable into two components. The write enable that you're bypassing and the write enable that you're stalling. And we're going to reintroduce these sort of two components here with two slightly different write enables, dependent on the decode of the instructions in the execute stage of the pipeline. OK, so let's do that. And we still have this term back in the stall signal. We still have this term in the bypassing signal. But we now have two different write enables, one for a bypass calculation, one for a stall calculation. And the bypass calculation, these two different signals are calculated based on the decode of the instruction in the execute stage. So we bypass only when it's a arithmetic logic unit or immediate arithmetic logic instruction, and let's say the destination is not 0. And we stall if it's a load or jump and link or jump and link register also falls into that case. And that's when we have to do the stall. Because the jump and link register, in at least this data path, we only have this multiplexer here, register 31 at the end. You could build data paths which have sort of different multiplexers for that, and you might be able to remove that clause from this. OK, so what we're going to notice here is our loads and jump and link registers and jump and links are going to stall when we have a match on the registers, and something like ALU instructions generating write enable bypass is going to not stall and use the bypass of the forwarding logic. OK, so let's take a look at what this looks like with a fully bypassed data path. So our fully bypassed data path, we're going to add all the destination locations. So out of here, we're going to run that back, and we're going to add two big multiplexers here. Because in our first case, we only multiplexed for the first source operand, or the A source operand. But we actually want to multiplex the inputs for A and B, the two source input operands. And we're also going to add this PC here for the jump and link that handles some of the more complex cases here, because otherwise we have to put multiplexers here for sort of R31 multiplexing in the PC or something like that. So we've effectively been able to bypass everything here. And the question is there still a need for the stall signal? So this is more than what we had before. This is more than just a source. We now can bypass out of not only here to there, but we can bypass out of after the memory operations. So maybe this changes our stall signal so that we don't need to stall on loads anymore. That'd be great. They'd have better performance. Well, unfortunately, no. we still need this. You still need to check if the opcode is a load in this stage of the pipe, even with a fully bypassed data path. So we've resolved a bunch of the data hazards, but the loads still need to wait, or instructions dependent on loads still need to wait because you don't know the result of the value until you come out of here, so you can't issue a subsequent instruction into the ALU stage early. You need to stall. But this is basically our full stall calculation at this point. Because we add all those bypasses, we've removed a lot of the other complexity from our stall signal. And in this case, you'll see that loads have a latency of 2 cycles. OK, so as I said, the last technique you can look at is speculation, where you try to guess things, guess data values, guess things like that, or try to execute code out of order. We're going to talk about that later in the course. That's not really in today's lecture. It's not really review material, but we will discuss that to some extent. So now we're going to move on to talking about control hazards. And because we're running a little late on time, we'll look at that a little bit more in next lecture.